Hello, AP Chem students, and welcome to topic 8.11, pH and solubility. This is the last section in the acid-base unit. So the learning objective for today is 8.11.a, identify the qualitative effect of changes in pH on the solubility of a salt. So this relates back to what we talked about in Unit 7 with the KSP values and solubility. So the pH of a system can affect the solubility of a salt in that system. So remember that low pH means that that there are excess H plus ions and therefore few OH minus ions, whereas high pH means that there are few H plus ions and therefore excess OH minus ions. So if you keep that in mind, the solubility depending on pH becomes an obvious application of Le Chatelier's principle. Now we're going to talk about this in two directions. The first one is an application in the same way that we already talked about it in Unit 7. So in the solubility of, for example, magnesium hydroxide, the solubility is affected by pH, and that's because of the presence of hydroxide. And so then if you have low pH, which means you have excess H plus ions, your added H plus combines with your OH minus ions here in the product to form water. And so it neutralizes some of the hydroxide, which removes hydroxide, which shifts the equilibrium towards the products to bring that hydroxide back into balance. That increases the solubility. Now, if you increase your pH, then that means you have excess OH minus, and then that does the same thing as if you added one of the components. You can treat this as really a common ion effect. So your added OH minus increases your concentration of OH minus, shifting equilibrium away from your products, therefore decreasing your solubility. Because what you've done in this situation is you have increased the concentration of your product, which means you have increased your Q value. And so you will shift towards the products to reestablish your equilibrium position. Whereas when you added hydrogen in the form of acid, that combined with OH minus, to remove OH, that decreases concentration. So that decreased our Q value, meaning we had to proceed towards the products to reestablish equilibrium and come back to our K value position. Now, there's a second way that pH can affect solubility. This one depends more on the topics that we learned in this unit. So if you have an ion that is a strong conjugate, okay, we particularly think about strong conjugate bases, that therefore will combine with H plus ions to make a conjugate acid or conjugate base ion, then here's a generalization for you. If the anion X minus is part of a weak acid, meaning it has a strong conjugate base, then the salt MX will have increased solubility in acidic solutions. And I want to show you why. And this would also, the opposite of this would be true if your cation is part of a weak base. Notably there, we think about the ammonium ion, which of course is the conjugate of ammonia. Okay, but I want to look at it from the weak acid perspective right now. So let's say that we have CaF2 that is dissolving in water. Now CaF2 has a pretty low KSP value, so it's not going to dissociate to a great extent, but it will just a tiny little bit. So let's say that we have CaF2. This is not proportional. It is proportional in terms of charge. It is not proportional in terms of KSP value. I just picked chose three molecules to dissolve because I thought it was enough for us to see the impact, but small enough to be able to count. So we've got our CaF2, and then we put them in water, and so they will dissociate like this. Most of them will stay in the solid form, but here we've got, so 1, 2, 3 calcium, 1, 2, 3, 4, 5, 6 fluoride, so that we have our balanced equation here. Now, so then that, if we count, then we've got those 3 and 6. Now, when the anion combines with the hydrogen in solution, so if you lower the pH, then what happens is you cause a shift in the equilibrium. So if you add hydrogen ions into the solution, hydrogen can bond with fluoride to form HF, which is a weak acid. So weak acids only partially dissociate. So not all of the hydrogen will bond with all of the fluoride if you gave it enough, but some of it will. And even most of it will. So then that would remove some of your fluoride ion because you'd have H plus X minus yields HX. And in this case, hydrogen fluoride. I think I've got, yeah, here we go. So H plus plus F minus yields HF. So that's going to remove some of your fluoride from the system and turn it into HF. So HF is not part of our equilibrium up here, and so it's not included in your K expression. And so what we've done is we have lowered the amount of F minus. So if we look here, up here we had 3 and 6. Now we have 3 and 5. So if this was our situation at equilibrium, we have now lowered the concentration. And so that means that it's going to proceed to products to reestablish the equilibrium position. So this is a way that you can increase the solubility. Okay, so that's how that works. Again, you can do the same thing with the base, but we do tend to see it more often with the conjugates of weak acids. All right. Oh, so then we have the shift. So I had a little arrow for. So what should you be able to do with this? First of all, determine if the solubility of a salt would be impacted by the pH of a solvent. And then secondly, discuss this impact qualitatively in terms of Le Chatelier's principle. What we see a lot in questions like this is they don't expect you to know off the top of your heads what are weak acids. So they would instead give you probably the solubility, and then they would tell you that it increases, the solubility increases and decreased pH or increases and increased pH or whatever. And it would ask you maybe to justify why that is. And then sometimes it will give you two different systems, equilibrium systems in the same problem. And one of them might be the weak acid equilibria, and then another one might be the solubility of a salt that has that conjugate that was originally set up in the weak acid system, if that makes sense. So if you're looking for extra practice on this, I will let you know that prior to 2014, every single question 1 on the free response was an equilibrium problem. And so you can go back and look for equilibrium problems on the test before 2014. They're published, they're out there, they're freely available with answer keys. And so if you Google like solubility, equilibrium, AP chemistry, you'll probably come up with one. But those are really great practice. The style of the question is a little bit different, but the main difference between those older style questions and the newer style questions is the newer style questions are a little more integrated in terms of content. So if you're really wanting to focus in on equilibrium itself, then going back to that question 1 on the old exam would be a really great way to do that. So that's it for today. That's it for Unit 8, and I'll see you pretty soon to start Unit 9.